There's a very interesting orbital requirement in the SN2 reaction that has some interesting consequences on stereochemistry, particularly for molecules that possess a stereocenter at the electrophilic carbon. So in this example down here, here's a stereocenter at the electrophilic carbon, and what we see is that the nucleophile can attack and displace bromine, and now we're left with a question of, does the methoxide end up pointing out at us after the reaction is done, or in the back? Well, as it turns out, it ends up in the back, and you can see why by taking a look at this orbital picture reflecting the transition state of the SN2 reaction, or I should say reflecting the earlier stages of the reaction before the transition state is developed. So the SN2 step is an N to sigma star, interaction. Here's the N orbital from the nucleophile. The sigma star orbital from the electrophile is here. And notice that in order to displace the leaving group, what we need to do is donate into the back side of the sigma star orbital. The front side has a very small lobe, and there's a node between the two nuclei right there. And so for optimal orbital overlap, the nucleophile wants to attack from the back side. And this is a phrase that you'll hear quite often, backside SN2, or backside nucleophilic attack. What the backside attack does is actually invert the stereochemistry at the electrophilic carbon. So this particular substrate is not chiral that we're looking at here, but if it were, then the configuration at that stereocenter would actually invert, and we'll see that for this example down here. So notice at the bottom of this slide that when the methoxide displaces bromine, we end up with the methoxide on a wedge, whereas we started with the leaving group on a dash, and that's a consequence of backside attack of the nucleophile on the electrophile. So take a look at this image here. What you're looking at is two substrates coming together to react in an SN2 type reaction. Imagine we had three different groups here. And notice what happens as the nucleophile approaches. You'll see the electrophile kind of do an umbrella flip, and that has the effect of inverting the configuration and making the new bond on the opposite side of sort of this imaginary plane formed by C, A, and B than the leaving group originally was. As a result, the stereochemistry inverts. So you can see that the electrophilic carbon essentially went kind of like an umbrella flip, right? It went from bowing outward this way to being perfectly flat to bowing outward the other way and forming a bond to the nucleophile. I wanted to give a couple more examples before we moved on of the importance of stereochemistry in the SN2 reaction. So you will sometimes see examples where SN2 is carried out intramolecularly, meaning within the same molecule, and you often need to be careful when this is the case. So for instance, say we had a molecule like this, where an alkoxide, is displacing the bromine. Now, you'll recall from our discussion of stereochemistry that we can assign the configuration of this, and if we do that, we would see that this would be position 1, this would be position 1, here's position 2 and 3. Placing the hydrogen towards the back, we would see that this is going counterclockwise. As a result, this would be the S configuration. Now the oxygen is still going to be the highest priority after the displacement, so we want to make sure that we end up with the R configuration on the product. So going ahead and just drawing the curved arrows here, we see that the product that we would get just in terms of connectivity is something like this. However, we want to know what's the stereochemistry at this stereocenter. Would we put that methyl group on a wedge or on a dash? Well, noting that we want to get to the R configuration, we could say, well, I'm going to try to put that on a dash or on a wedge, excuse me, and put the H on a dash and see what configuration I get. So looking at this, the oxygen would be priority number 1, here's priority number 2 and 3. In this case, we're actually still the S configuration, right? It's still counterclockwise to go from highest to lowest priority. As a result, we know we need to switch the configuration at that stereocenter, and we can do that by simply changing the wedge that we drew to a dash now, and placing the hydrogen on a wedge. And now if you work out the RS configuration for yourself, you'll see that this is indeed the R configuration, and we have inverted the stereochemistry relative to the starting material. So just to review very quickly, the SN2 reaction involves the replacement of a nucleofuge. The nucleofuge is another word for the leaving group that takes electrons with it. So in the example down here, the nucleofuge is the bromide right here, and it's replaced by a nucleophile, which donates electrons in to form a new carbon X bond typically. The favorability, so whether an SN2 reaction is reasonable to propose or not, is governed by the relative stability of the nucleophile and leaving group. Essentially, this boils down to the acidity of their conjugate acids, whether HBr, in this case, is more acidic than CH3OH. We know it is, as a result, we would favor the forward direction here. We saw how the N to sigma star frontier orbital interaction forces backside attack of the nucleophile on the electrophile. This has some interesting stereochemical consequences in that it inverts the stereochemistry at the electrophilic carbon. Next time, we'll take a look at nucleofuge dissociation, which is an interesting step that bears a lot of similarities to the SN2 reaction, except it takes place in the absence of a nucleophile, and it represents sort of half of the SN2. So it's simply the dissociation of the nucleofuge on its own. In some naming conventions, SN2 has been called a combination of nucleophile association, which is another step we'll take a look at, and nucleofuge dissociation. Next time we'll take a look at nucleofuge dissociation, and then in the lecture following that we'll look at nucleophile association, and you'll see why this order has been chosen in a couple of lectures.